Hello everyone, welcome to this week's algebraic graph theory seminar. Today, Ralihe will tell us about the determinantal ideas of a graph or graphs.
Thank you so much for inviting me. So glad. Okay. So I'm gonna talk about pretty much the main topic of my research. So I wanna try to give you like a general framework of it, and in particular, a couple of things I've been working lately. So let me start with things we all know, spectral graph theory. So given any graph matrix, like the adjacency matrix, Laplacian matrix, or we're thinking also about the distance matrix, we can think about the spectrum of each one of these matrices, and we say the two graphs are m-cospectral for any of these matrices if they have the same spectrum, and two graphs are generalized m-cospectral if they are cospectral for this particular matrix, where G is the all ones matrix. For every real value phi. So in particular, Johnson and Newman proved that two graphs are generalized and cospectral if and only if they are cospectral for that particular matrix for two values of t. So it's not necessary to check for every value. We can talk about two values. So for the adjacency matrix, that's to say that two graphs are generally m-cospectral if and only if they are cospectral, and also their complements are a-cospectral. But that's not necessarily true for distant matrices. So I like to present these two results because they serve as motivation together with something else I'm going to talk about for some of the results on determinantal ideas. So if we think about the spectrum of a graph, we can think about graphs whose least edge value is greater than -2 or -3 or a given number. And there are very nice known results about this characterization of graphs. If we impose more conditions, like for instance, if we talk about the strongly irregular graphs with least eigenvalue at least with least eigenvalue equal to -3, then we have this characterization in particular. So we want to find analogous results for determinantal ideas of graphs, but I'm gonna get to it. But first, let me talk about another diagonal form of any given graph matrix. So if we have the adjacency distance matrix, we can think about the semi-normal form over the integers, or in general over any principal ideal domain, or even more general, what we want is to have a good behavior on the greatest common divisor of two elements on a ring. So the semi-normal form is a diagonal form given by elements which divide each other, not each other, but this one divides the second one divides the third one, and so on. And those elements in the diagonal are called the invariant factors of this semi-normal form, or of the matrix in particular. And we find this semi-normal form just by performing elementary operations, but over the integers. So that means interchanging two rows, add a multiple integer of a row or column to another, and multiply a row or a column by 1, which doesn't do nothing, or -1. And actually, there's a theorem, the elementary divisors theorem, which says that the k invariant factor can be computed by the greatest common divisor of the k minors of the matrix. So you take a matrix and you think about the determinants of the submatrices of size k by k, that's the minors. And then we compute the greatest common divisor, and we can compute the invariant factors from there. So actually, its normal form can be found in polynomial time, just like the spectrum. So this minimal form is connected with a sample group of a graph. So one can say a lot of things about the sample group of a graph, connections, combinatorial connections with chip firing games on a graph, which are also connected with the tubed polynomial, with nice fractal patterns, and so on. But I'm not going to talk about that. That's another talk. The Mathematics of Chip Firings by Carly Clevans is one of the best, if not the best, reference for it. So algebraically, the sample group is nothing but the torsion part of the co-kernel of the Laplacian matrix. So it's this quotient group, actually, where L sub n is the reduced Laplacian. So that means take the Laplacian and erase any row and column, corresponding row and column. And actually, the sample group is isomorphic to this group right here, which is given by the invariant factors of the Laplacian matrix of the graph. So it's mean normal forms connected with sample groups. But besides this connection of this mean normal form with chip firing, it seems like problems with these mean normal forms are more algebraic than combinatorial. But we're trying to find applications of mean normal forms, of way of using mean normal forms that are helpful for determinantal ideas. So it is a known fact that two matrices, A and B, are similar over a common field, if and only if their characteristic matrices, these type of matrices, have the same mean normal form over the principal ideal domain ring of these polynomials. So, okay, so I talk about spectral graph theory, its mean normal form, sample group, but what is a determinantal ideal? So instead of defining determinantal as ideals for any given matrix, let me go directly with this particular matrix. So let's think about the generalized Laplacian matrix. So what we do is that we take the diagonal matrix given by n variables, and then we subtract the adjacency matrix. So instead of writing the degrees in the diagonal as with the normal Laplacian, we write variables. And then what we do is we compute the ideals generated by the k minors of this matrix. So that's what determinantal ideal is for graphs, or at least how we define it. So instead of taking the generalized Laplacian, we can take any graph-defined matrix. So in particular, if we take this matrix, we call this the critical ideals of a graph. And as we can see, so for the minors of size 1 by 1, we have ones always if we are thinking about connected graphs. So except for the trivial graph, we always have an edge. So we always have a 1, and that means that the first critical idea has a 1. So it actually generates the whole polynomial ring. right? So this is actually the whole polynomial ring. So the second critical idea, if we have something like this minor is 2 by 2 minor, that's a 0. But if we can actually find some minor like -1, -1, 0, -1 that gives you a 1, then the second critical ideal will be 1 as well. But maybe we can find that one, right? And for sure, at some point, we're going to have a critical ideal that is different from the whole polynomial ring. In particular, the last critical ideal is the ideal generated by the determinant of the matrix, right? So that polynomial, the determinant of the matrix, is called the critical polynomial of the graph. So for instance, Dino Lorenzini proved recently that this critical polynomial, if we think about all the values that it takes, as we take x1 up to xn greater or equal than 1, actually all those values are 0, 1, so all the natural numbers, including 0. So this polynomial is of study right now. But now, okay, so I talk about critical ideals, but we can play with these variables, right? We can think that all the variables are equal. We can set off just some of those variables equal, some not. But for instance, for this particular example, when we take all the diagonal with the equal variable, then we have the characteristic ideals. And notice that now the end characteristic ideal is called like that because we have the characteristic polynomial of the adjacency matrix of the graph. So for instance, so one fact is that if two graphs have the same critical ideals, then they are isomorphic because this critical polynomial is very strong. So actually, on the critical polynomial, we can see if one h is there or not. So that gives us that it has to be unique for each connected graph, for each graph, actually. And for instance, if we have all the characteristic polynomials equal for two graphs, then in particular, we know they have the same spectrum because they have the same characteristic polynomial. Now, if we keep changing this, and now we use the distance matrix, then to those ideals, we name them, we define it as distance ideals. So now we take the distance ideal, the distance matrix of a graph, we place variables on the diagonal, compute the minors, and think about the ideals generated by these minors. So these are the distance ideals. So I don't know if this polynomial has a name, to be honest, but just name it the generalized distance polynomial. So if any one of you know, please let me know. So we can do this, and we can also think about the univariate distance matrix and so on. Distance ideals. So this is an example, right? So let's keep thinking about a house graph. And if we compute the characteristic ideals and the critical ideals, they are quite different. Notice that the ring matters, okay? So I'm using the notation I, K of G, regardless of the ring, or if I'm using A or the distance or any other matrix. Choose for the purpose of this talk, I'm gonna be specific in each case. But the thing is that the ring matters. So these are the ideals. If we compute this over the integers, but they change if we compute it over the reals. So maybe over the integers, we have like a sub 4, like the fourth characteristic ideal is equal to the ideal generated by t plus 2, comma 5. But then when we go to the reals, we can see that we can multiply that 5 by 1 over 5, and we have a trivial ideal, let's say. So if we call this trivial. So now that we know what determinantal ideals are, let's think about some properties. So for instance, if we define as gamma k, the graphs with the most k critical ideals equal to 1, and as lambda k, the graphs with the most k distance ideals equal to the whole ring, then the determinantals, notice that the determinantals ideals preserve the induced graph order. So that is that for critical ideals, if we have the G is an induced graph of H, then the K critical ideal of G is contained on the K critical ideal of H. And for distance matrix, for the distance matrix, that's a little bit different because we need distance hereditary graphs. So a distance hereditary graph is a graph in which distance is preserved between inductive graphs. So that's a strong statement. So we define the algebraic rank. So if we are thinking about graphs with the most k critical ideals trivial, then let's think about this parameter, the maximum k such that the k critical ideal or distance ideal or determinantal ideal is trivial. And in this case, if H is an induced graph of G, I'm changing the order, sorry about that, then the algebraic rank of H is at most the algebraic rank of G. For adjacency, again, for distance, we need distance hereditary property. Moreover, we know that since the induced order is preserved, then this set of graphs is characterized by forbidden induced graphs. And that's also true for small values of k when we are thinking about the distance ideals. So that's a thing. So it worked for 1 and 2, and I think it works for 3. That's work in progress. So a good question is for which k this doesn't work. And if it actually works for every k, why, right? How come? But actually, I think it breaks at some point. So I'm going to talk more about that in a minute. Also, the algebraic rank has been related to the minimum rank problem or zero forcing in spectral graph theory, just to mention it. So talking about spectral graph theory again, we know that two graphs are n-cospectral if and only if they are co-determinantal for this matrix. So this direction is very easy because if two graphs have the same, so I mean with co-determinantal, sorry, I mean the same determinantal ideals, same critical ideals in this case, for instance. If that happens, sorry, characteristic ideals. So if that happens, the characteristic polynomial is equal for those two graphs, and therefore they are cospectral. So it's this direction with needs a little bit more argument. So if two graphs are cospectral, then actually the last determinantal characteristic ideal are equal, the characteristic polynomials are equal, but also it's true for every other determinantal characteristic ideal in this case. And in particular, they have the same algebraic rank. So that's a nice result. And actually, we can talk about generalized M-cospectrality, and that happens if two graphs have the same determinantal ideals for this matrix. And as well as we are talking about spectrum, we can talk about having the same Smith normal form. So we call those graphs coinvariant graphs. So two graphs, G and H, are M coinvariant if they have the same Smith normal form. But actually, by the theorem of elementary divisors, two graphs are M coinvariant if and only if they have the same determinantal ideals for this matrix over the integers. So notice that if we evaluate our vector of variables on the diagonal of M, and we know the critical ideals or determinantal ideals of the graph, then we know that that's generated by the greatest common divisor of the matrix. So in this way, we can prove things like the fact that the star graphs are characterized by the Smith normal form of certain type of matrices. So for instance, star graphs are characterized by this Smith normal form of the distance Laplacian, and a lot of results like this with the help of determinantal ideals. So by characterizing the set of graphs with the most k ideals trivial, we can characterize the family of these graphs of graphs who has sandpile groups of which are highly uncyclic. So what I mean is that if we have graphs in which the first determinantal ideal is trivial, as well as the next k minus 1 determinantal ideals are trivial, or in this case, critical ideals. Then we know that the first k invariant factors of the Smith normal form are equal to 1. So the Smith normal form of the Laplacian has k ones. And then by characterizing the graphs in which the k plus 1 invariant factor is different than 1, we can characterize the family of graphs whose sandpile group looks like this. Also, knowing the structure of the critical ideals for certain family of graphs can be useful. So for instance, we can characterize the sample group for outer plane graphs, because every time we have any outer plane graph, like this one, then if we think about its plane dual, that is the graph defined by placing one vertex in each one of the faces, and then every time you have an edge between those two faces, you write an edge. So something like that. So actually, the sample group of an outer plane graph, and actually every planar graph, if we think about its dual graph, but then we reduce it, meaning we erase the vertex corresponding to the outer face, then for outer plane graphs, we know that this is always a 3. So it turns out that the sample group of another plane graph is isomorphic to the sample group of a given tree. Or sometimes that tree can have multiple edges, but that still works. So what we do is that by a known result of Valencia and Corrales, where they characterize the critical ideals for trees, we can find the sample group, the characterization for the sample group of trees. So I won't say much about this, but the point is that it's very combinatorial. You take the tree corresponding to the dual, erasing the outer face, and then think about that tree with loops. And then you think about the two matchings on this graph, this multi-graph. And then using those minimum two matchings over this graph, you can find then the greatest common divisor, taking big matrices and then just choosing the matrices corresponding to loops on those two matchings. Anyway, the point is that there's a lot of combinatorial structure on critical ideals, and that can be seen in some families of graphs, and that's helpful to compute some stuff like the sample group of trees or others minimal forms for trees. So if again we think about this type of matrices, which are defined like this, so you take that transmission, that's the sum of the distances in each vertex on the diagonal, subtract the adjacency matrix, you can compute this minimal form from the combinatorics that we found or that were found for trees. So has all these connections with different stuff, mainly by the spectrum, mainly by this minimal form. So now I want to talk about graphs with few trivial determinantal ideas. So this will help us to then characterize graphs with whose sample group has few invariant factors equal to 1, or even more than that, these graphs whose minimal forms for the distance matrix or other matrix have few invariant factors equal to 1. So for instance, a graph has only one trivial, only the first trivial critical ideal, if and only if that graph is a complete graph. So this is the characterization by forbidden inductive graphs. On the other hand, a graph has only the first two critical ideals equal to the whole polynomial ring, if and only if it's a complete tripartite graph, or it looks like this, where this is the empty graph. So I like to draw this as an independent set. And then you have a click, another click, and this edge means that every vertex here is connected with every vertex here. So this is the characterization using a set of forbidden inductive graphs. So actually, with this, we know that the graphs with whose sample group have at most one invariant factor equal to 1 is again the complete graph. And from here, we know that the graphs with the most whose sandpile group sorry, so let me write as the semi-normal form of the Laplacian has only two invariant factors equal to 1, and the third one is different than 1, and so on. If we want to think about graphs that whose sandpile group or semi-normal form for the Laplacian looks like that, then all those graphs are complete tripartite graphs or graphs of this form, but we have to be specific about values of m, n, and p. Like for instance, for a tripartite graph, m and n has to be greater or equal to 2, and so on. So it's just a subset of this family of graphs. And for the set of graphs with the most 3 critical ideals trivial, there are only partial results at this moment. Like for instance, thinking about a specific clique number and things like that. And actually, this is forbidden induced set. A set of forbidden induced graphs for that set, for that family of graphs. So actually, here we are thinking with the black vertices, we have cliques, and with the white vertices, we have independent sets. So all of these are forbidden induced graphs, and we think these actually characterize the problem, but still to find that characterization is difficult. So now if we think about characteristic ideals, so that means take all the variables equal, then G has at most 1 trivial characteristic ideal, again, if it is complete, has at most 2 trivial characteristic ideals, if it is a complete or inducible graph of a complete tripartite graph. So these sets are actually subsets of what we saw previously. But if we are thinking about characteristic ideals, we can actually characterize the set of graphs with at most 3 trivial characteristic ideals. So those are the cycle of length 5, of size 5, the triangular prism, a complete 4-partite graph, or a graph that looks like this, or like this. So from here, notice that we can also think about sandpile groups, but when we think about sandpile groups, now we have to, again, impose more properties on the graphs. So we don't go as far as strong regular graphs. We just say regular graphs. So this characterization gives us a characterization of regular graphs with a sandpile group and with the most 3 invariant factors equal to 1. Again, it's just a subset of this. So you have to compute the 4th invariant factor and check about that. So in particular, this gives us C5, a complete graph, complete bipartite graph, complete tripartite graph, complete 4-partite graph, a regular, and this graph right here, this graph right here, that again has to be regular. So all those graphs have a sandpile group with the most 3 invariant factors equal to 1. So now if we move on from adjacency to distance, things change a little bit. So if we think about the set of graphs whose distance ideals, so whose first distance ideals is trivial, but the second is not, then that's again a complete graph. Or now it's a little bit bigger, an inducible graph of a bipartite graph. And that's defined by this set of forbidden inducible graphs. Moreover, again, if we change our ring, so the ring can be the integers or can be the reals, notice that we can also think about the rationals. But in this case, thinking about the rationals is equivalent to thinking about the reals. The reason is because any coefficient that appears on these polynomials are actually integers, because we are just taking the adjacency matrix, distance matrix, and so on. So in this case, we can say rationals, reals, and it's the same thing. If we use other type of matrix like normalized Laplacian or something like that, then it's different to think about rationals or reals, right? But in this case, it's the same thing. So a graph has at most one trivial distance ideal over the rationals or the reals, if and only if it's a complete graph or is this particular type of bipartite graph. So that's star, right? We also have worked a little bit with directed graphs. So that impose no symmetric graphs, makes things a little bit more difficult, but some characterizations have been possible. So recently we have been working about, on the graph with the most two trivial distance ideals. And this one is interesting because there's a few things we know. The first one is that if a graph has a most two trivial distance ideals, then shouldn't have any cycle of length, of odd length, greater or equal than 7 as an inducible graph. And also we know that it shouldn't have any of these SUV matrices. Sorry, SUV graphs. Also, notice that there is known that the semi-normal form of the distance matrix of a tree looks like that. So that's 2 1s, and then only 2s up to the last diagonal, until the last invariant factor, which is 2 times n. Right, so that's a way to prove Graham and Pollack and Lava's formula for the determinant of a distance, of the distance matrix of a tree. So because of that, we know that it has at most, trees have at most 2 trivial invariant factors, or 2 invariant factors equal to 1 on its minimal form. Therefore, trees actually have at most 2 trivial distance ideals. And again, we know that distance ideals, graphs with the most 2 distance ideals are all whole trees for 7 or larger, and are free of all these graphs. So actually, we were able to prove that the set of graphs that are free of poles of length 7 or more, and free of all those particular graphs, it's characterized as follows. So it has to be a cycle of length 5, of order 5, or it has to be a bipartite graph. So here is not a complete bipartite graph. We're thinking about any bipartite graph. So this is saying that, okay, so let me not get ahead of myself. So, okay, bipartite graphs, complete tripartite graphs, partite graphs, multipartite graphs that looks like that. So every partition consists of only one vertex, except for one of those partitions. Or it looks like that, like this, right? So this is an independent set. So it's an independent set, and every one of these edges, again, means that every vertex here is connected with every vertex here, and so on. So it looks like 5 or 6. And actually, some months ago, we didn't know how to approach this problem, but turns out that work done on graphs free of certain sets of inducible graphs, it's very helpful. So, for instance, if something that it's easy to see is that if a graph is house free, that means it's free of this graph, then it has to be anti-odd hole free. So that means the complement of cycles of odd length. That's easy to see. And so we just think about more lemmas, like if a graph is free of odd holes of order 7 or more, and it's different than the cycle, then G has to be a perfect graph. So in particular, we can see that if G, if the cycle of length 5 is an inducible graph of G, then just by checking the set of forbidden subgraphs, we see that G has to be C5. So then we can think about C5 as another forbidden inducible graph. And then by this lemma and by the strong perfect graph theorem, by Chudnovsky, Robertson, and Seymour, and Thomas, we know that the graph has to be perfect. So perfect means that the coloring number is equal to the clique number for the graph and for every inducible graph of G. And Chudnovsky, Robertson, Seymour, and Thomas prove that that's true. So a graph is perfect if and only if is free of odd holes of length 5 or more, and also free of anti-odd holes. So this is an important lemma that we use. Other lemmas, like the fact that if a graph is pole-free, meaning free of this graph, then G has to be triangle-free or a complete multipartite graph. So let me jump the schedule to proof because of time. So the point is that we use this, we use another claim, more lemmas on characterization of graphs by forbidden induced subsets. And we arrived to the fact that G is free of all of those graphs and free of cycles of odd length greater or equal than 7, if and only if it's one of these graphs. So what we prove is the characterization of this type of graphs. So we prove that a graph is free of all those subgraphs if and only if it looks like any of these any of these 6 type of graphs. But then to actually have the theorem, which is that a graph has at most 2 distance ideals trivial over the integers, if and only if it looks like any of these graphs. We have to do a little bit more. And that is, we need to show that every induced subgraph of every graph listed in the term have non-trivial third distance ideal. So at this point, that's doable. Like for k equals to 2, that's doable. But as we go higher, that's more and more difficult, probably, well, surely. So one way to do this is to find, so one way to do it is actually compute the third distance ideal, which is the most difficult way. Another way to do it is to find an evaluation of the variables on a vector such that the tri-invariant factor of that particular matrix is not equal to 1. So if we can find this evaluation, then that means for sure that the third distance ideal is not trivial. Because if it is trivial, then we have to have 1. So for the bipartite graph, we can prove that every minor of size 3 of the distance matrix is an even number. So this, in a way, hint on a generalization on the semi-normal form result for threes. So Graham, Pollack, and Lovelace formula and the formula for the semi-normal form of distance matrix of threes seems to be more general. So it's not just about threes, but in a way it's for bipartite graphs. There's still work to be done to specify this generalization. But long story short is that the semi-normal form of the distance matrix of a bipartite graph has its third invariant factor equal to 2. And then also it comes a lot of 2's here. And if we play with the evaluations of the diagonal, we can say more, but let's say it looks like that. And the amount of zeros has some combinatorial explanation. So anyway, so for the rest of the graphs, so every non-bipartite graph, we can determine the semi-normal form using the structure of twin vertices. So that means, So that means if we take, for instance, a complete tripartite graph, what we do is think about the distance matrix of this graph. But with a certain evaluation. So on all of these vertices, we set it up to 2. So every time we have a vertex in one of these independent sets, notice that the distance for any of these 2 vertices is equal to 2. So in this case, we can think about that diagonal form. And when we compute the semi-normal form of this, what we find is that on all of these independent sets, so we can think about this as twins. You can say false twins because they are not connected. All those 2 in the diagonals, so something, and then we have 2's everywhere else, actually. It's just 2 times j, 2 times j. Right, and then we have 2 times j, 2 times j. And then we have the distance to every other one. And that's J, J, J. So the point is that by using elementary operations, we can find that this is equivalent to just taking this graph with that evaluation. And that works. Don't remember if this is 2 or 4, exactly what, that, for the mean normal form, sorry. So it's diagonal of 1, 1, and 2, let's say. But the point is that that works. And actually, if we take any of these subgraphs and we set up the diagonal entries corresponding to these vertices to 2, and here to 1, 2, and 1, everything works out because of the distance matrix form. So that's what I mean that we use the twin structure of the graph. So actually doing this process, we can find a lot of graphs whose, for instance, the fourth invariant factor of the distance matrix is, sorry, the first three are equal to 1 and the fourth is not, and so on. So we can actually find a lot of graphs that look like this or something similar for the next set of graphs and so on. So actually, this is a way in which the behavior of this mean normal form help us to work with something that used to be quite more difficult, more when we were trying to compute a third distance ideal, which we are still doing for some cases. But in this particular case, over the integers, with these properties, it helps us. So just to say a couple more results. So if we use instead of the integers, we use the the reals of the rationals, we can also find a characterization. So in this case, it's a little bit different because we don't have this mean normal form to help us so much over the reals. So what we do is actually compute a trier distance ideal for over the reals. But there are some tools that can help us in this case to make things easier. And if we go to univariate distance ideals, we can also find a characterization, which is easier. So these ideals on these mean normal forms over the integers can help us to do extensive descriptions of infinite families of graphs for these sets, even when K is big, which was not really approachable before. And actually, it kind of tells us something maybe deeper. So there's a lot of work, conjectures regarding the form and properties of determinantal ideals, of critical ideals using twin vertices. And we now have a new conjecture on distance ideals, but using twin vertices and pendant vertices that relate to the previous work. And I can say more, but my time is off, I think. Thank you.
Thank you, Raleigh, for the talk. Do we have any questions? So for the critical ideals, it's characterized for k equals 1 to 2 on the integer.
Right. Right. So
How
it's
about the
characterized.
rationally?
Right. So it's characterized over the integers for 1 and 2, and for 3 is still not done. You have all of these forbiddance of graphs, but it's not yet characterized. But for the rationals or reals, it's also characterized for these two cases, but
Yeah.
not for this case.
The same work is done for the distance one, the similar result.
That's right. And another thing I should mention about the distance ideals is that it's funny how everything works using inducive forbidensus graphs, even though the distance hereditary property is not fulfilled by a hypothesis. But turns out that there's something going on that, at least for small case, it's always you always end up with distance hereditary graphs or with funny things like this bipartite case. Yeah.